Hello and welcome to lecture 9, and as you can see the title today, crash course on hydrogen atom first, and then we will be subsequently applying the perturbation theory tools that we have developed so far to understand something which is known as fine structure of the hydrogen. Now all of you know that whenever there is something new, you need to basically do a background work, some kind of net practice. So before jumping to something new regarding hydrogen atom, let us do the net practice first. That means let us do the basic reviews on the hydrogen atom, on whatever you have learned so far. So the hydrogen atom Hamiltonian is first of all known to you. You have already obtained the bound state spectrum and have learned that there is a large number of degeneracies that exists for all states except the ground state. Now, as I said, we will remind ourselves of few very basic things which some of you might have already known, but some of you may not have seen this in this manner that I am going to discuss right now. Now, to start with, therefore, the hydrogen atom Hamiltonian, which for later purposes I will denote with H naught. That means essentially this will be our unperturbed Hamiltonian in the later part of the discussion. We will write it as p square by 2 mu minus e square by 4 pi epsilon naught r. So the first term here is the kinetic term, where this p is basically the three-dimensional momentum vector, and the second term is the potential energy. And this, of course, if you use it in the position space, it should look something like minus h dash square by 2 mu minus into grad square operator minus e square by 4 pi epsilon naught r. This r is the operator. This object here is the operator because we are doing quantum mechanics. Now keep in mind for your atomic and molecular physics course, which you are having it parallelly, that instead of a single proton in the nucleus, suppose you are considering a nucleus of charge Z times E, which is the nuclear charge, where Z is called the atomic number, which basically tells you what is the number of protons and neutrons in this nucleus. The total nuclear charge is Ze, and it is still orbiting a single electron of charge minus E. So we are considering a scenario where we have a central charge, which is basically the charge of the nucleus is Z times E, and then there is some single electron which is orbiting this nucleus. So where can we get this scenario? We can get this physical scenario when we are considering ions such as helium plus, which is for basically Z is equal to 2. You can also think of ions like lithium 2 plus, which is for Z is equal to 3. So in these cases, you have a nuclear charge which is Z times E, but you have a single electron orbiting. So in those cases, you can simply modify your unperturbed Hamiltonian as minus h slash square by 2 mu grad square minus Z times E square by 4 pi epsilon naught into 1 by r. Now let us talk something about this mass mu. The mass mu is usually taken to be the mass of the electron. Y is usually taken to be the mass of the electron. But since, it's not originally taken to be the mass of the electron only, because if you consider the hydrogen atom, then there is a proton and there is an electron. So why should you take the mass of the electron only? But because this is a two-body problem, As you already know, it is basically more correct to think this mu as a reduced mass. So let me just remind you what the reduced mass was. So it was just the mass of the electron times the mass of the proton, which I denote here by capital M, and then mass of the electron plus the mass of the proton. Now this, of course, you can write it as me times capital M, and then you can take this capital M common and write it as 1 plus me by capital M. And because this capital M is much greater than mass of the electron, because proton is extremely heavier compared to the mass of the electron, so we can always do this, or we can always write this as me into 1 minus me by m, and therefore this will become me minus me square by capital M. Therefore, of course, your mu should be roughly represented as me, simply because me square is much less than the mass of the proton. For example, in case of, if you take the example of the hydrogen atom, where the nucleus is a single proton, and there you have mass which is the mass of the proton, which is basically 1836 times the mass of the electron. So you can easily see that how heavy a proton is. Now the Schrodinger equation for the eigenvalue problem that we want to look here is basically this H naught psi is equal to E n naught psi. So this is the problem that you have already solved in PH 204, your quantum mechanics 1 course, at least for Z equal to 1, that is for hydrogen. So Z equal to 1 is the hydrogen atom you have done in PH 204. Okay, so that is the assumption. Now the solutions were of this form. If you may remember, these solutions of this were psi nlm r theta and phi. We solved this hydrogen atom problem in the spherical polar coordinate because the system has a spherical symmetry, and the solution had a radial part which depended on the principal quantum number n and the angular momentum quantum number L, multiplied by the spherical harmonics ylm theta phi. So if you remember, these RNLRs had a name, and they were called the generalized logger polynomial. So these were the polynomials. The differential equation corresponding to the radial variable gives you a polynomial, and that is the logger polynomial, and ylm theta phi, as already also known from your central force problem in quantum mechanics, are the spherical harmonics. Now, as you already know also this fact that the states are labeled by 3 quantum numbers, which are written here. Quantum numbers, which are the principal quantum number, the orbital angular quantum number, and the azimuthal quantum number. And these take integer values in the following range. So n can take values, integer values, positive integer values 1, 2, 3, like this in integer steps. L can take values from 0 till the n minus 1th value, and m can take values from minus L to plus L. Now also another thing which is very much familiar to you, you already know about the energy eigenvalue once you have solved this problem. The energy eigenvalue or eigenvalues, they only depend on this principal quantum number n, and they go as 1 by n square. So if I write this En0, this will be minus z e square by 4 pi epsilon naught whole square mu by 2 h cross squared into 1 by n square. As already discussed, n are positive integers, we denote it by like this. So this object is the most important object presently in our discussion. Why? It will be clear now. So this energy eigenvalue, of course I have written not for the hydrogen atom. If you put capital Z to be equal to 1, you will get the results for hydrogen atom. This object actually can be written in terms of something which is known as the Bohr radius. So the Bohr radius, if you remember, was defined as 4 pi epsilon naught h slash squared by mu times e squared. This was called the Bohr radius. What did it say? It is basically a length scale which signifies the most probable distance between the nucleus and the electron in the hydrogen atom in ground state. Okay, so that's what is the physical significance of this Bohr radius. So this is the most probable distance between nucleus and the electron in the hydrogen atom in ground state. Now once you have defined this Bohr radius, which has the numerical value of 0.0527 into 10 to the power minus 10 meters, this is basically a, if you look at this A naught, it is nothing but a constant which is made out of the quantities h cross, the reduced mass or the mass of the electron and the charge of the electron. So in terms of this Bohr radius, you can write down this En0 in the following manner. This should be minus e square by 4 pi epsilon naught into 1 by twice A0 into n squared. So this is also another expression which might need our attention at some later stage. So let us number all these equations. So 1, 2, 3. Now in fact this also can be sometime written as, okay, I mean while writing this I have simply written this for z equal to 1 case only. That means this I have written for z is equal to 1, but you could easily generalize it for any z. I have written this because we are going to use this for the hydrogen atom only as an example. Now there is another way of writing this energy, and that is going to be crucial for our discussion. So let us actually define something which many of you are probably familiar with. That is a constant again, which is defined as e square by 4 pi epsilon naught into h bar c, which is called alpha or denoted by alpha, and it has the value 1 by 137, which is known as the fine structure constant. Why do we need it? I will come to that, but this is a very important constant in the context of our discussion. So, if you define alpha to be in this manner, then immediately you can write down the En0, the unperturbed energy value, in the following manner: Z alpha whole square into mu times c squared divided by twice n square. So this is again the same energy we have written by defining another constant which we have termed as the fine structure constant. This is also a very important quantity which we will see now. Now you notice something peculiar in this expression. You notice this appearance of the c in this expression of En0, which is basically nothing but the speed of light. And this was required in the expression of En0 in order to cancel the appearance of c in the definition of alpha, the fine structure constant. Now the reason for writing this in this manner is that the quantity alpha is a dimensionless quantity. If you look at it, it is a dimensionless quantity. Alpha, the way we have defined, you can check, is a dimensionless quantity. And as I said, it's called the fine structure constant, and it should be thought of as the way to characterize the strength of the electromagnetic force. You note this appearance of E square here. So everywhere when you discuss the electromagnetic force, Coulomb law, you have this factor of E square. So alpha in some way basically tells you about the characteristics of the strength of the electromagnetic force. And this E square is being divided by h cross and c to make it dimensionless. Also you can note that we have treated the hydrogen atom in the previous quantum mechanics 1 course, that is in pH 204, non-relativistically. So in principle c should not enter in it, and the kinetic term was just p square by 2m when you wrote down this Hamiltonian. Okay, so when we wrote down this Hamiltonian, we just remember that in our pH 204 course we only actually wrote down the kinetic term as p square by 2m. There was no hint of any kind of relativity or anything. Now, the energy scale which is relevant to the bound state spectrum can be better appreciated using the speed of light to consider both the fine structure constant alpha and the rest energy of the electron. It's a complicated statement, so let us understand this statement a little bit carefully. As I said, alpha, the fine structure constant, was defined as E square by 4 pi epsilon naught h bar c. So that is our alpha. And what was the rest energy of the electron? Rest energy, all of you are familiar from your PH 101 course, the special theory of relativity part of it. Please recall that part. In fact, it is nothing but mass of the electron times the square of the velocity of light. In fact, in this case, this is nothing but mu c square, because for our purpose, mu is which is the reduced mass, is nothing but mass of the electron. So let us look at this quantity. 1 by 4 pi epsilon naught E square by the Bohr radius. I can write this as E square by 4 pi epsilon naught. Let us actually write down what this A naught was 4 pi epsilon naught h bar square divided by mu times E squared. So this was our Bohr radius and we are dividing it by A naught, and we have E square by 4 pi epsilon naught whole square, because A naught has 1 4 pi epsilon naught factor, and then we have mu times E squared from this expression of A naught, and then 1 h bar square in the denominator. But what is this? This is nothing but exactly mu, and then you note this e to the power 4 by 4 pi epsilon square h cross square. If I can put 1 c square in the numerator and in the denominator, then I can simply write it as mu alpha square into c squared. So that means this is nothing but alpha square times the rest energy of the electron. So therefore, what does it tell us? It tells us that the energy scale of the hydrogen bound state is a factor alpha square smaller than the rest energy of the electron. I am denoting everywhere electron by E minus. And if you want to look at the magnitude of this smallness, it is about 19,000 times smaller. Wow. So that means essentially why it is like that. Again, let us recollect from this previous expression which we had already written, hopefully. So let us again number 4 and this is 5. So we had somewhere written this expression here in terms of the Bohr radius. So En0 in terms of the Bohr radius was E square by 4 pi epsilon naught into 1 by 2a0 1 by n. And now we can simply write it nothing but minus half mu c square alpha square, and there should be 1 n square, because our 1 by 4 pi epsilon naught E square by a0, this whole factor is sitting here, E square by 4 pi epsilon naught 1 by a0, which I have just replaced. So we have got this expression. There was 1 n square, so this is wrong. Yeah, so this is therefore nothing but minus half alpha square mu c square. Again you see that this is the rest energy, and then there is this 1 by n square term. So if I finally write down En0, I can get an expression of this object which in terms of alpha and the rest energy, it looks something like this. So this is a very important expression, and let us number this equation 6. So what does this tell us? This is the expression of the Bohr energy which you have already calculated. So Bohr energy are of the order of alpha squared. So already you see we are treating this alpha as some kind of a parameter in terms of which we are trying to figure out different quantities. Now let us actually take a look about something different. The typical momentum in hydrogen atom, suppose this, we are considering this Bohr radius, and if I simply write down the uncertainty relation, then I know that P times A naught should be of the order of H cross. So P should be of the order of H cross by A naught, right? So this is just by the use of uncertainty principle. Okay, delta P delta X is greater than equal to H bar, but we are just using the result very roughly to get some rough estimate. Now what is this H cross by A naught? If I simply put the expression of A naught, this is nothing but mu E square H cross divided by 4 pi epsilon naught into H cross again. H cross squared. So this will turn out to be mu E square divided by 4 pi epsilon naught H bar. And again you see that this is nothing but E square, let us write it like this, by 4 pi epsilon naught H bar C, and then we have mu times C in the numerator. So this is again alpha times mu times C. So P is almost of the order of alpha times the rest energy of the electron. It says that the typical velocity, what does it mean? It means that the typical velocity of the electron, which is nothing but of the order of alpha times C, which is low enough, because alpha is just 1 by 137, which is low enough that the non-relativistic approximation is more or less accurate. And finally, I want to also mention something, that you note that, again let us write this expression of the Bohr radius. These are very important scales, length scales, that you should never forget. 4 pi epsilon naught H cross square by mu E square. And I mean, in this whole discussion, we will be alternatively writing either mu or m subscript E or me, just to denote the electron mass. The approximation that was done, I have simply described it at the very beginning of this lecture. So this you can write it as 4 pi epsilon naught H bar into C, and there is another H bar, and in the denominator let us write it as mu times E squared and another C to cancel the C in the numerator. So what does it give? See, this object 4 pi epsilon naught H bar C divided by E square is nothing but 1 by alpha. So this gives us H cross by mu times C into alpha. So this is again in terms of the rest energy of the electron times alpha. So this is, but we can interpret this in the following way: mu C into 1 by alpha. This is nothing but H cross by MEC, mass of the electron times C, into 1 by alpha. But what is this object H cross by MEC, mass of the electron? This is nothing but the reduced Compton wavelength, reduced because we have changed the, or we have approximately taken the reduced mass to be equal to mass of the electron. So what does this relation tell us? This tells us that Bohr radius is kind of over a 100 times, because your 1 by alpha is just 137. So the Bohr radius is kind of 100 times larger or bigger than the Compton wavelength of the electron. Now let me very quickly go to all these whatever we have just discussed will be required later, but let me very quickly go to some definitions which are also very important. Now the energy spectrum, you have already read that it can be seen experimentally as spectral lines, right? These are due to excited electrons which are dropping from one state n to some lower excited state which is denoted by m, say, where m is less than n. And while dropping from higher excited state to lower excited state, the electron emits a photon. So there is a photon which is emitted of frequency which is denoted by h bar omega, which is the energy level differences between these two levels. So these are all known to you. And you also know that when the electron drops down to the ground state, so when electron drops down to n equal to 1, which is nothing but the ground state, the resulting spectral lines are called Lyman series. When electron drops down to, so this should be m, because m is less than n always, so m is equal to 1 is the ground state. So, and when the electron drops to higher states with m greater than 1, the sequence are or sequences are referred to as Balmer lines or Balmer series, Paschen series, and so on and so forth. Also, again, this is for your spectroscopic atomic and molecular physics course. In spectroscopy, instead of referring the angular momentum quantum number L to label the states, they are sometimes referred to by some letters. Okay, so for example, L equal to 0, 1, 2, 3, like this, and you will see that in books, or mostly in chemistry books, you will see that they are called as S, p orbital, d orbital, f orbital, like this, s, p, d, f. These are kind of old fashioned way of naming, and they come from observed quality of the spectral lines. This S is nothing arbitrary. This S is the full form, the full form of S is basically sharp. This P stands for principal, D stands for diffuse, and F stands for fundamental. So in this way, just by observing the spectral line and their nature, people have named these things. Now let us come to a very, very interesting and important aspect, because this is going to be the bread and butter for our rest of the discussion. That is the degeneracy, because when we will apply perturbations, degeneracy is going to play the most crucial role here. Now, what are the degeneracies here? The fact that this En0 depends only on n and not on any angular quantum number L and m means that each energy value is degenerate. It has to be degenerate, because your En0 did not depend on L and m. It only went as 1 by n square. No dependence on other quantum numbers which are L and m, which immediately implies that each energy value is going to be degenerate. And we already know this thing, but let us remind ourselves how can we quantify this degeneracy. To quantify this degeneracy, let us recall this thing. I am not going to the detailed discussion. So we have obtained some relation when we discuss the hydrogen atom in detail, that this small n, which is the principal quantum number, is equal to capital N plus L plus 1. If you may remember, this came while we discussed the radial equation, the series solution. So this capital N was always greater than or equal to 0. And what did it imply? It actually is the degree of the polynomial, Logger polynomial, generalized Logger polynomial in R that appears in a wave function. In fact, it is nothing but number of nodes or zero crossings in the solution of radial equation for the hydrogen atom. It's a three-dimensional equation. As you might remember, there was a radial part, you applied the separation of variable technique, and there was a radial dependence and then theta phi dependence. The radial dependence would lead to the Lager polynomial, and the theta phi dependence will lead you to the spherical harmonics and all those things. And what was this L? This L was basically again greater than or equal to 0, can take values, and if in fact it represents the angular momentum of the state in which we are in. And this equation tells us that for each value of L, for each fixed value of n, that suppose we fix the value of n, you can actually see by looking at this expression. Suppose I want to fix this value of n, L ranges from 0 to n minus 1. For fixed n, L ranges from 0 to n minus 1. And then for each fixed L, m ranges from minus L to plus L. So these are the important observations that you can have. Now therefore, what should be the degeneracy here? The degeneracy, of course, you have calculated it. Degeneracy, of course, is going to be basically, this means that what is the number of states with the same energy En0. So you have fixed this n in En0 and try to figure out what are the number of states. So it is nothing but a summation over L from 0 to n minus 1. Remember, L can take values from 0 to n minus 1 only. And 12 plus 1 is the number of m values, because m can take values from minus L to plus L. So if you do the summation, it will give you n square. But now, is that all? That is what you first ask. But of course, this is not all, because each electron also carries a spin degree of freedom. Remember, spin also is a degree of freedom, and you have to include that spin degree of freedom. And therefore, that means that it is measured along when the spin is measured along a given axis, the spin can either be up, which means the quantum number ms is half, or it can also be down, that means ms is minus half. So including this spin, the degeneracy of the state with the fixed energy En0 corresponding to a fixed value of n, the degeneracy becomes 2 times n square. So that's what is the total number of degeneracies that you can have. Now let me just very quickly draw one important figure here. So this is basically to represent something interesting. So we have this S, P, D, F, all these orbitals. What does this mean? This means we are considering L equal to 0, L equal to 1, L equal to 2, L equal to 3 states. Now let us start from n equal to 1 because n equal to 1 is the ground state. If you look at this expression for n, then for n equal to 1, when you fix n equal to 1, you know that L cannot be anything other than 0. So your L is also fixed. That means capital N can only be 0. So you have a state which will have n equal to 0. Then for small n equal to 2, you will have this kind of labels. For n equal to 3, we will have, for n equal to 4, we will have capital L n's like this. So in this manner. So this is basically n equal to 2, n equal to 3, n equal to 4, and you can go above like this in this manner for all these different capital N values. So this is your n equal to 0. Then you can have n equal to 1 and n equal to 0. You can have n equal to 2, n equal to 1, n equal to 0. Corresponding to, of course, you have to remember you have fixed these L's here. For example, let us take n equal to 3. When n is equal to 3, look at this equation. When n is equal to 3, small n equal to 3, you know that L can take values 0, 1 and 2. Now when n is equal to 3 and L is equal to 0, n can only be 2. So your n is equal to, small n equal to 3, L equal to 0, n is 2. Similarly, you can figure out these values corresponding to these n values and small n values and small l values. Here, for example, this is n is equal to 3, n is equal to 2, capital N is equal to 1, capital N equal to 0, like this. So any hydrogen eigenstate specified by the 3 quantum numbers small n, small l and small m will thus have the value of n fixed. That's what this picture tells you. Now let us look at the general form of the wave function also, because that is also very important. So the general form psi n l m r theta phi, it is going to have some constant. Then if you remember, it has a factor of r over the Bohr radius to the power L. It was multiplied by a polynomial in r over the Bohr radius, the radial coordinate by the Bohr radius, which was of degree capital N, which was being multiplied by e to the power minus r by a naught into n, and finally you will also have y lm theta phi. So this was the generic structure of the hydrogen atom wave function. Eigenstates were of this form. And remember, this capital N was nothing but small n minus L plus 1. And this capital A was the normalization constant. So now look carefully at this expression. The value of n you can actually read off from the exponential factor here. Suppose I give you the general eigenfunction of this form. You can actually, by looking at the expression, you can figure out which values of n, l, m are these eigenfunctions representing. For example, if you look at these exponential factors carefully, it will tell you what is the value of small n, the principal quantum number. The value of small l, the angular momentum quantum number, can be read from the radial prefactor. This is the radial prefactor. If you look at this factor, you will be able to know what is your L, or it can also be figured out from this YLM theta phi. And value of small m can actually be read off from only this YLM theta phi value. So this is how you can, just by looking at the general eigenfunction, can figure out what are the quantum numbers, which state actually is being represented by this general eigenfunction. So that's what I wanted to discuss about this, but let us actually come back to the degeneracy. Let us ask this very basic question: where did these degeneracies come from actually? So the question is, where did these degeneracies come from? And of course, you know the answer. Usually, this degeneracy or any degeneracy is related to a conservation law, and as you all know, these conservation laws in turn are related to the symmetry. So we have to think about this Hamiltonian H naught, which we had written minus h slash square by 2 mu del square minus 1 by 4 pi epsilon naught z e square by r. We have to think of what different kinds of symmetry are there in this Hamiltonian or in the system in general. So let us think about them. The most subtle degeneracy to explain is the fact that energy does not depend on L. That is the first interesting fact. Energy does not depend on the orbital angular momentum quantum number. And this follows from a special symmetry of this Hamiltonian. This Hamiltonian has a special symmetry, and I am sure it was discussed in your PH 204 course. If not, we can discuss it later. So this special symmetry, it's basically a conserved symmetry which is called the Laplace-Runge-Lenz vector, Runge-Lenz quantum vector. And this ultimately follows from kind of a hidden SO4 symmetry in the formulation of hydrogen atom. Therefore, any deviation from the form of H naught, the unperturbed Hamiltonian, will lift the degeneracy of L. That is the first very important point. So we ask this question that energy does not depend on angular momentum quantum number. Why is that? And the answer is, this is because of a special kind of symmetry which is represented by a vector which we call Runge-Lenz vector, which hopefully was discussed in your PH 204 course. If not, we can discuss it later. But now you also ask, well, my degeneracy is not only related to the orbital angular momentum quantum number, it is also, there is a degeneracy in M also, which is the azimuthal quantum number. So from where does this degeneracy in M come from? So degeneracy in M follows from the very simple rotational invariance. So we are dealing with a system which has rotational symmetry, and correspondingly there is conservation of angular momentum, and we don't therefore expect it to be lifted unless something breaks the underlying rotational symmetry of the problem. So this M symmetry, this is the symmetry which corresponds to the rotational symmetry of the problem. Hydrogen atom has rotational symmetry, and therefore your angular momentum is conserved. So until and unless you do something which breaks this underlying rotational symmetry, that degeneracy in M is not going to be lifted. But then we also have seen there is a overall factor of 2 in the 2n squared degeneracy, which of course came from the spin S. So 2n square, the factor 2 comes from spin, considering the spin. The degeneracy must therefore follow from the conservation of spin. In fact, if you think about this problem again, this H naught, each eigenstate of this H naught, the unperturbed Hamiltonian representing the hydrogen atom, is really two degenerate states, one with electron spin up, another with spin down. And these states are degenerate because H0 does not have any explicit dependence on spin. So the degeneracy must therefore follow from the conservation of spin. But as you all know, there is no such conservation law. Spin is just another form of angular momentum. The only thing that is really conserved for this whole system is the total angular momentum, which is J equal to L plus S. Total angular momentum is conserved, not the spin only. So any addition to this H naught which recognizes that only J is conserved will lift this degeneracy. So suppose you add some term which basically recognizes this fact that J is conserved, therefore it is going to be lifted, the degeneracy is going to be lifted. So we will have to supplement this unperturbed Hamiltonian H naught, which we have written here for the hydrogen atom, with extra terms that correspond to corrections that arises from relativity and from the spin of the electron. That's what this whole discussion so far tells us. And what it will give us? What will it give us? It will actually give us, which is known as hydrogen atom fine structure. So that's what we are going to get if we consider relativity as well as this spin. And how we are going to do that, that's what we are going to tell right now. So for that, once again, let me very quickly write this minus h slash square by 2 mu del square minus e square by 4 pi epsilon naught 1 by r. So let us actually again use the numbering. 6 was the last number, so let us write 7 here. So we have already seen how to correct for the motion of the nucleus. What did we do? We just simply replaced this mu by mass of the electron. Okay, that's what we have done. Now more significant is the so-called fine structure which we have just mentioned here. What is this fine structure? Which is actually due to two distinct mechanisms. Let me write those. One is something which is known as the relativistic correction. We will see that very soon. And the another one which is basically the known as the spin orbit coupling. Now, compared to the Bohr energies, which we have just discussed at the very beginning of this lecture, fine structure is a tiny perturbation. It's always smaller by a factor of alpha squared. Alpha, remember, was 1 by 137, which was the fine structure constant. Now, that is regarding the fine structure, but you can still have another factor of alpha, and that is called lamp shift, which is associated with the quantization of the electric field. Of course, this is not in the purview of this course. I am just mentioning these things. And in fact, even smaller by yet another order is called hyperfine structure. Okay, so just for the sake of our discussion, let me write these names here. So first thing that I said is that compared to Bohr energies, fine structure is a very tiny contribution or perturbation, and it is smaller by a factor of alpha square, smaller than the Bohr energies. Compared to the Bohr energies, it's smaller by a factor of alpha square. Smaller still by another factor of alpha square, that means total alpha cube, is the Lamb shift. Is called some phenomena called Lamb shift, which is basically related to the quantization of electric field. Of course, quantization of fields is something which is not under this syllabus, so we cannot unfortunately discuss this. And finally, there is even smaller terms or smaller correction by yet another order, those are called hyperfine structures. We started with fine structures. There are something called hyperfine structures to hydrogen spectrum, and this is basically due to the magnetic interaction between the dipole moments of the electron and proton. This is related to, or this originates because of magnetic interaction between the dipole moments of the electron and proton. So this is, of course, you already know that these Bohr energies, these are order alpha square. We have seen at the very beginning. So if the fine structure is smaller by factor of alpha square, then fine structure would be of the order of alpha to the power 4. So therefore Lamb shift, this Lamb shift therefore will be of the order of alpha to the power 5, and hyperfine splitting will be another order higher, alpha to the power 6. Okay, so what we are going to do is that we are going to discuss this relativistic motion first. So correction due to relativistic motion of electron in hydrogen atom, and we are going to see what are the corrections that arises because of the consideration of the relativistic motion of the electron. Now at the very beginning, let me just give you a kind of a warning that you can run into difficulty if you naively try to incorporate special relativity into quantum mechanics. When we say relativistic motion, that immediately means that we are going to use special relativity, but we cannot simply naively try to incorporate special relativity in quantum mechanics. It creates a lot of problems. To do things properly, exactly the way it should have been done, is that you need to work in the framework of quantum field theory, and you also need to know the Dirac equation, both of which are beyond the scope of this course, of course. However, What we are only going to be interested in are the scenarios where the relativistic effects are thought of as small corrections on the original results we have already obtained in pH 204. That means we are going to think of these relativistic effects as corrections over the energy spectrum that we have obtained, as corrections over the energy eigenvalues that we have obtained in pH 204, which we have already treated non-relativistically. Now, in this situation, it is usually safe to stick to single particle quantum mechanics, and it is also safe to use perturbation theory. So, the first and foremost relativistic shift of energy levels comes simply from the fact that the effective velocity of the electron in an atom is a substantial fraction of the speed of light. From your pH 101 course, you must be remembering that the energy of a relativistic particle is basically given by square root p square c square plus m square c to the power 4. Now, if we are considering the hydrogen atom, then the kinetic energy, let us denote by T, which has two parts basically. Suppose we start from the beginning again. These two parts basically tells us, one tells us about the kinetic energy of the electron, another tells us about the kinetic energy of the proton divided by 2mp say. So this is the term which is kinetic energy of the electron, this is the term which represents kinetic energy of the proton. Now we use the relativistically correct expression for electrons kinetic energy, where the kinetic energy basically is nothing but this total energy, which is Pe square c square plus me square c to the power 4 minus the rest energy. So that is my Te, me c square. This is the rest energy, me c square, and this is the relativistic total energy. And now what you do is that you do this trick that this is me c square, and then we have suppose 1 plus Pe square by me square c square minus 1. So this object, this Pe is compared with MEC, and MEC is much larger compared to this electron momentum. So we can expand this binomially, and what we obtain is MEC squared. Then we have 1 plus half Pe by MEC squared minus 1 by 8. We are doing a binomial expansion. Pe square by me squared, or let me write it like this, Pe by MEC whole to the power 4 plus dot 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 minus 1. And of course this gets cancelled, and what we are left with is Pe square by 2me squared minus 1 by 8 Pe to the power 4 divided by me cube c square plus order Pe to the power 6. So this is my equation number 8. So this is what we have obtained, and interestingly, of course, you would expect this to happen. The first term here is nothing but the kinetic energy of the electron in the non-relativistic level. So this is basically your P square let us write this as 2 mu. Okay, so this mu and me, we are always, sorry, this should not be 2 me square. Me gets cancelled. This should only be me. So this is p square by 2 mu, and we'll always have to remember that mu and me are basically same. This is my kinetic energy, non-relativistic kinetic energy term. And the kinetic energy operator therefore has this part, and this can therefore be thought of as some perturbation. Now we already had this proton kinetic energy term, but you can already neglect this relativistic correction to the proton's kinetic energy simply because mass of proton is much greater than mass of electron. So this is neglected for relativistic correction. It will have this non-relativistic p square by 2m, and together it will give you this reduced mass. Now, so the Hamiltonian, which is unperturbed, was already written in equation 7. So let us write down the full Hamiltonian then. H is written as h naught plus h1. Let me write this small r to represent that it is basically relativistic correction. So we have this as p square by 2 mu. Instead of writing p subscript e, we are writing just p because we do not want to complicate things with all the subscripts now. And then we have e square by 4 pi epsilon naught r. It was our h naught. And then we have this minus p to the power 4 8 m e cube c squared. The interesting thing is that despite the fact that hydrogen atom is highly degenerate, we can still use the results of the non-degenerate perturbation theory. So this is the most interesting thing. So this is, of course, the most beautiful equation that we have arrived at so far. So the next interesting thing is that despite this fact that we all know that hydrogen atom has high degeneracies, and we can still use the results of the non-degenerate perturbation theory. Why? It is because the perturbation is spherically symmetrical, and therefore it commutes with L square and Lz operators. So the perturbation H1r commutes with Lz operator and L square operator. So we have found out these two operators which commutes with unperturbed Hamiltonian H naught and the perturbed Hamiltonian H1r. Moreover, the eigenfunctions of these operators taken together have distinct eigenvalues for these degenerate n square states with the eigenvalue En 0. So we can therefore pick our unperturbed states as the ones which are the simultaneous eigenstates of H naught and L square Lz. That is, we can still work with our standard Kates, which are the eigenstates of the unperturbed Hamiltonian, which sometimes is denoted by NLM Kate or psi NLM, it doesn't matter. It's just a convenience of notation. They are the unperturbed eigenstates. But as it turns out that because we have figured out these operators which commutes with H naught and H1r, these psi NLMs are also the good states for the problem, and NLM are the good quantum numbers. Therefore, even though there is degeneracies, the theorem that we had proved earlier, remember we had proved this theorem, If I am able to figure out some operator omega which commutes with H0 and H1, then, and if this operator omega has distinct eigenvalues in this basis, therefore we actually do not need to diagonalize the Hamiltonian, the perturbed Hamiltonian. The Hamiltonian is automatically diagonalized in the same basis. So that's what is happening here. So we have not been bothered about the degeneracy at this level. So what should be the formula? The formula for calculation should be En, and we are just going to remove this degeneracy of L. So let us just keep this L as the subscript and this first order correction due to relativity. So this is what the formula is, psi NLM. We know that this will be the perturbed Hamiltonian and then another psi NLM. These are the unperturbed eigenstates. So this is going to be minus 1 by 8 me cube c squared psi NLM, and let us write this as p square into p squared operator psi NLM, and this is going to give us minus 1 by 8 me cube c squared, and using the hermiticity of p square operator, p square psi NLM, we can write this psi NLM. Because we have already seen that the perturbation is diagonal in the psi NLM basis, so we can always do that. Now to simplify our evaluation, we will do a trick, we will use a trick. What is that trick? We are going to use the Schrodinger equation. So note the Schrodinger equation is the following: p square operator by 2me plus the potential, kinetic plus potential operator, energy operator, psi NLM is going to give us En0, the unperturbed eigenvalues, times psi NLM. So it tells us that p square psi NLM, it gives us p square psi NLM in terms of this En and V operator. En is just some energy eigenvalue, it's numbers, but V is an operator. So this is 2me En0 minus V operator acting on psi NLM. So we are going to use this in place of p square psi NLM. So what do we get here? We get the following. We have ENL, this is equal to minus 1 by 8 me cube c squared. We are writing this as 2me En0 minus V psi NLM, 2me En0 minus V psi NLM. This is equal to, we will have this 2me into 2me, that is 4me square in the numerator now, divided by 8 me cube into c squared. We will have En0 minus V psi NLM, En0 minus V psi NLM. Now the operator En0 minus V is also Hermitian, and it can be moved from the bra to the ket. So we can write this as minus 1 by 2me into c squared psi NLM into En0 minus V, En0 minus V psi NLM. So we will be getting this object minus 1 by 2me into c squared Now we know that this V is an operator, but E is just some fixed value for a particular n, fixed number. So this is not an operator. So En0 squared, when this En0 multiplies this En0, then there will be terms like En0 into V operator minus V operator into En0 plus V operator squared, everything together acting on psi NLM. But this En0 is just some fixed thing. So En0 into V operator and V into En0, V operator into En0, they are same. So I can always take this En0 to the left side of V, and I can write this as, let me write the final answer, 2mec squared. So En0 square will remain there, and then there will be something like minus 2En0 expectation value of the V operator in the NLM state, and then V square expectation value in the NLM state. So that's it. So here we have used the fact that psi NLMs are orthonormal, that means this is equal to 1, we have written this. So the problem therefore has been reduced to the computation of the expectation value of the potential energy operator and potential energy operator square in the state psi NLM, which is now for, with an experience of yours in PH 204, it's just a very easy task. So the expectation value we have to calculate, the problem has been reduced to expectation value calculation for V and V square operator. So that we will do in the next class, and we will then go to the next portion of this discussion. Okay, so we will first calculate these expectation values and see what are the contributions from this relativistic correction, and then we will go to the next part of our discussion.